right, everyone. I am here with Arun Kumar. Arun is an associate professor at the University of California, San Diego. Arun, welcome to the TWiML AI podcast.
Thank you for having me, Sam. It's a pleasure to be here.
I'm looking forward to digging into our chat. You work at the intersection of databases, database management, and machine learning and AI. Certainly lots of interesting ground to cover there. But to get us started, I'd love to have you share a little bit about your background and how you came to work in the field.
Yeah, certainly. Yep, like you said, my research is at the intersection of data management systems and machine learning and AI. My PhD is from the University of Wisconsin-Madison in the database group there. I moved to University of California, San Diego in 2016 after graduating there. And I'm jointly affiliated with both computer science and data science here at UC San Diego. And my research started out in the database area. So I started working on information management and kind of tools and systems for that. And over um, my graduate school research, I started working on machine learning and database systems. And this was with Professor Christopher Ray when he was there. And afterwards, I switched advisors and I worked with Professor Jeffrey Naughton and Jignesh Patel, continuing to work on this area of looking at how do you scale machine learning algorithms to larger than memory data? How do we build tools to make machine learning easier to use, easier to kind of deploy? And have collaborated with companies such as Microsoft and Oracle and Google and so on. Um, and so this intersection of data management systems and machine learning was really exciting for me because it was a greenfield space. The database community has studied scaling of data intensive computations for 4 decades. And so now, as machine learning becomes mainstream, people want to apply it to large and complex data set, it just seemed like a natural fit for where my research should go. And so that's sort of how I got into this space since my grad school days. So I've been working in this space for about a decade now.
Awesome, awesome. And you refer to this again, at least in your talk or some of your past talks, as the DBification of ML and AI, which suggests that there's a migration or a an evolution of machine learning and AI towards incorporating more database capability or functionality. How do you think of that that evolution?
Yeah, sure. I can explain that. So the term new DBfication is something that I cooked up earlier this year when I had to give a talk at ICDE for an award they gave me. And I was thinking about what exactly is happening in this area, and that was the term I could come up with to describe it. The reason I call it that, and this is something I will talk about in the DBA workshop as well, is back in the 80s when relational algebra and SQL started taking off, people realized that there's a lot of things that are needed to make it practical. There's scalability, there's manageability, usability concerns, and so on. And making these sorts of systems easier to build. That is when the relational DBMS community started to form. And now, 40 years down, it's like a very mature community. There's like $100 billion plus industry per year, right? And so many companies in the space that are trying to make relational SQL computations practical and user friendly. In the ML space, that is sort of the change that we need to see. Making ML
Okay.
computations scalable, manageable, usable, and making these sorts of tools easier to use and develop. That is what I call the DBfication. So, whatever transformation the research community did to relational SQL computations over the last 40 years, we need that to be done to ML computations and ML workflows and end-to-end ML applications. So that is what I call DBfication of MLAI. So these concerns of usability, scalability, manageability need to be tackled.
Awesome, awesome. And in that sense, it's a bit of a meta commentary on kind of where we are in this state of time in ML and AI relative to where databases was some period of time ago.
A- Absolutely.
But there's also a an aspect of your research that deals with the relationship between the fields and how databases support machine learning workloads, and I'm guessing help provide some of these characteristics that you described, scalability, et cetera. How do you see the relationship between the two?
Oh, yes, certainly. So this is also something I will cover in my talk is the evolution of the landscape of ML platforms. And one of the periods in that evolution is what are called in-RDBMS ML toolkits. This is a field that has been studied for 20 years now. Back in the early 2000s, Oracle, Microsoft, IBM, and all these relational DBMS vendors decided to add support for machine learning and data mining algorithms on top of their relational DBMS platforms. And the target users were like enterprise analysts who would like to keep the data in their relational databases rather than having to export them to flat files and then run them on separate things. And then that kind of leads to a manageability nightmare. And so they said you could run these machine learning computations in the DBMS process space. You could invoke them from the SQL console or something like that. And so that work still continues. There's a community that studies that sort of stuff, and a lot of my work is also focused on that in the past. In the last half a decade or so, the community has really expanded beyond that. There's work on ML on data flow systems, which also comes from the database and systems communities, stuff like Spark, Spark MLlib. There's work on custom ML systems now. That's a new research community that has formed at this intersection. You have these tools like XGBoost, and then of course these deep learning systems like TensorFlow and PyTorch, which very similar to kind of database systems in the way you specify computations at a higher level. They have compilers and optimization stacks that translate it to hardware specific kernels. So there is this analogy of what data systems are in the ML landscape versus what they were in the relational landscape. But now people are realizing to make ML more practical, you have to really look beyond just the system stack for training and inference. You need to look at governance, you need to look at provenance, you need to look at data transformations and preparation, data labeling, and model deployment. So these end-to-end ML platforms such as MLflow and TensorFlow Extended and SageMaker, they have also started to come about. And I think all of these sorts of tools stand to learn a lot from the relational database world. And that's one of the reasons why I'm excited about this workshop. So at the SIGMOD conference, which is one of the top database area conferences, we've had the data management for end-to-end ML team workshop, which looks at this sort of intersection. But now we want to bring that to the ML venues as well. And hopefully the ML community can also get excited about what does ML look like in practice? What does ML look like at scale? And what are the sort of data management issues in the end-to-end ML context?
So walk us through your talk. How do you open your talk and contextualize uh, the the relationship between the fields?
Sure, absolutely. So first of all, I motivate that ML and AI are no longer just arcane academic endeavors. 10 years ago, NeurIPS was probably the hangout spot for mathematicians and statisticians mostly. Now, if you look at it, it's like 10 times larger, 15 times larger. And it's so hard for me to look at the entire program. And it's a hangout of big tech companies, a huge number of papers from tech companies, other enterprise companies, smaller web companies. So it's become a ubiquitous business critical need. And so there are pressing problems of usability and scalability that need to be tackled to help democratize machine learning. So that is sort of the motivation for this larger area of work. We want to democratize machine learning by tackling these pressing issues of both human productivity and human efficiency. So people involved in the loop, like data scientists, ML engineers, MLOps people, and also system resource efficiency, making things cheaper, faster, and easier to use, that sort of stuff. And so this is where I believe that the database and systems communities can bring a lot to the table and tackle these issues of um, system efficiency and human efficiency. So that is sort of how I motivate the stock. And then I draw analogy to the database community's work in how they help democratize relational and SQL computations. Like nowadays, when you want to perform, say, data record retrieval or update transaction or aggregate statistic for, I don't know, sales forecasting or something like that, you don't sit and write C++ code. You write one line SQL code. You write, probably use dashboards and business intelligence tools. Whereas if you're going to do ML, you're going to be sitting writing what, Jupyter notebooks. You're going to be writing low-level Python code, using libraries and stitching functions together here and there, using Airflow scripts and stuff like that. So that sort of state of the art is often a mess in production. So some of the lessons that we had from the database world on how do we commoditize data software systems, that needs to be translated to the machine learning world. And so I go over across the entire life cycle of machine learning applications. I divide that life cycle into three stages: sourcing of data, building of models, and deployment of prediction pipelines. The sourcing stage is where you convert raw data in your data warehouses, data lakes, database systems into what I call ML ready data. That is where you go through the process of acquisition, transformation, preparation, labeling, and cleaning and stuff. Then you have the building stage where you do the feature engineering, model selection, hyperparameter tuning, all of these things. And then you have the deployment stage, which is where you integrate it back into your application, which could be on the web, which could be on IoT devices, or in your data warehouses. And then you have to monitor and maintain these models as the application evolves. So I decompose the study of the space into these three large kind of high level stages because the concerns for the software systems and the concerns for the users across these stages are very different. In the sourcing stage, a lot of the work is still very manual. There's very little scope for kind of automation that can be end to end because there's just so many bespoke issues that happen with data preparation and cleaning and labeling and so on. So there are some tools that are coming about to improve productivity of people in this space. And that is an area I think that the database community's expertise with data integration, data cleaning, data provenance, workflow management, and query languages and APIs, all of that can help. Then comes the build stage where you need really high throughput execution of ML computations. Resource efficiency, you want to make sure you use your clusters and your GPUs optimally as close to as possible. And that is where the systems issues come into play. And so translating stuff into faster executions using query optimization techniques, using compilers techniques, using scalable data systems techniques like parallel database systems and data flow systems, cloud native executions, these sorts of things really matter. And so that also is an area where the data systems community has a lot to help. And then finally, in the deployment stage, I think there is a lot of issues in MLOps. How do we productionize these sorts of pipelines, end-to-end pipelines, again, provenance management, debuggability, explainability. There is a lot of software engineering issues there. So like the software engineering for ML space, data engineering for ML space, I think there's a lot of open questions in those arenas as well. So that is sort of the overview I give. And then I dive into two specific research projects from my research that are exemplars of both the sourcing stage and the building stage. That's primarily where my research is focused on.
Got it. Got it. Thinking about the analogy that you're making between the database in general, database systems, and ML and AI, and the ML and AI workflow, um, it strikes me that in a lot of ways, even though databases, can be, large and complex, they are more or less, single purpose, in the sense that they're there to store data and, return it in response to some set of queries. Whereas the machine learning workflow, as you've identified in these three different stages, is those stages are have very different sets of requirements, and the overall workflow, it's hard to reduce to a single thing that it's doing, in the same way. I'm curious how you think about, that impedance mismatch, maybe in the analogy.
One thing to note is in the relational database world, people focus on the RDBMS primarily as the engine that kind of answers SQL queries. But there's a whole stage called ETL that goes before the data even gets loaded in many cases. And so the sourcing stage is analogous to ETL in the database world. People don't tend to highlight on ETL stacks, but now ETL, reverse ETL, ELT, all these are hot areas of research and kind of startups that are coming about in the database industry itself. I mean, why did Hadoop take off? Why did MapReduce take off? It's because database people underappreciated the importance of ETL. And that's sort of what we've learned over the last decade. And so now you have Spark and data lakes and data lake houses. They kind of bridge this gap between the querying stack and the ETL stack. And so now you could operate on raw file systems. So there's a lot of innovation happening in that space as well. Now, coming to ML ops, I think there has been in the past companies that wanted to do data ops as well, which is delivering data to kind of websites and IoT devices that are near real time. And that whole data ops space is kind of what led to innovation in the key value stores landscape, like Amazon.com, Facebook.com. These are websites that have profile data that need to be updated in real time. And so that's sort of why key value stores came about. And now people are realizing with things like feature stores, you need some of that again. You need to have data ops, delivery of data in near real time. Now, ML ops is obviously more complicated than that. The ETL that is needed for ML is obviously more complicated than what people did for database ETL. Um, However, some of the principles and tools, I think there is a lot to learn from in that landscape. Coming to the analogy with the querying system, so you have RDBMS stack where you have SQL console and you train it and you can you get your query answered. The analogy for that would be like model building systems, like a TensorFlow or PyTorch or XGBoost. You don't need to write ML algorithm implementations for these. You just give the data, you specify the invocation in their APIs, they build a model for you. And they do this at scale, they do this in parallel if needed. They may not do it that well. Some of the deep learning tools still fail to scale on models or data for many reasons. But that is sort of the analogy for the RDBMS stack for the SQL console itself. And then you, in the database world, you also have this whole stack of data integration and business intelligence tools and visualization tools. You need all of that for ML too, because you need to do monitoring, you need to do maintenance of the workflows, you need to do access control and governance. And so that sort of stuff would also, you'd have to see the analog come about in the ML landscape.
Got it. Got it. So part of the analogy is encouraging us to zoom out from the database and look at this broad ecosystem of tools that evolve to support kind of end to end working with data. And, we can see a lot of the same things happening on the machine learning side.
Exactly. Yep. So in the database community, it's not just the RDBMS like optimizing SQL queries. There's all these other topics that people have been studying for decades now. In the ML world, there's been intense study on scaling ML algorithms in particular, and new model architectures and new ML algorithms, new optimization procedures. I think they need to zoom out and then look at the end-to-end ML workflow and look at the end-to-end ML application lifecycle and start studying these sorts of auxiliary issues that are also critical and that are now the main bottlenecks for many adopters of machine learning.
In some ways, thinking about the end-to-end machine learning workflow and MLOps, they seem like software engineering challenges as opposed to research challenges. But of course, there's a broad research community that is thinking about these issues too. What's the role of research in thinking about these, more production types of issues, tools issues, etc.?
Yeah, that's a great question. My frank answer would be I do not know much about that space as much as people who are actually working in industry. And this is something that I've had conversations with several folks, Shreya Shankar and Chip Huyen, Sarah Catanzaro, and several others, Goku Mohandas. I invite them over to my classes to give kind of guest lectures, meet with them at conferences to understand this space. I am not running and operating a giant ML production platform. So I don't get to see the kind of ML ops issues that happen in the deploy stage of the life cycle. And this is something that academics in general face because they don't run these billion user services that companies face. Um, Now, coming to the issue of software engineering for ML, I think there is both a research community and a practice oriented issue there because there is a research community around software engineering in academia too, and they publish at venues such as ICSE and FSE and so on. They try to understand the principles of software engineering. I think looking at that from the ML kind of software engineering for ML standpoint, there is some research issues to be studied there from the software engineering research world. Now, in the practice world, practitioners who kind of build these sorts of tools and pipelines and then kind of deployment infrastructure, what will help is for them to kind of think about what are the more generalizable questions beyond their particular company, beyond their particular use case or pipeline. Are there challenges that can potentially be surfaced to the research community that can lead to kind of a virtuous cycle that will lead to better tools in the future? I think that would be an interesting avenue for collaboration between researchers and practitioners. And I think these workshops of this sort, and also the industrial conferences like the Spark AI Summit that I went to, Strata, that O'Reilly ran before the pandemic, those are sort of great venues for these sorts of conversations to take place. A lot of practitioners usually don't show up to research conferences because it's not that relevant for their work. But now I think a lot of practitioners are showing up to NeurIPS and ICML, and they want to kind of interact with the research community to tighten that kind of to kind of make that loop faster. So hopefully we will see more research come about in the MLOps landscape from the academic and industrial research worlds as well. And rather than just building tools and open source developments, which is also important, but for longevity, we need to understand the more fundamental principles and the technical challenges at a more general level than just a pipeline or a stack that they build for their particular organization.
You mentioned that section of your talk is reviewing a couple of projects that you and your research group are working on. Can you introduce us to those?
Absolutely. So, bulk of my research in the last half a decade has focused on the source and the build parts of the lifecycle, the data preparation issues in particular, and the model building issues for deep learning. I can talk about the latter first. So that is Project Cerebro. So these are the two exemplars that I give in my talk at the DBA workshop. Now, the Cerebro project was launched based on a single observation that many people who are building these ML systems are focusing on building one model at a time. And so they are thinking of stuff in a very low level manner. What I have learned from my conversations with ML practitioners at over 3 dozen enterprise, web, healthcare, domain science, and many other settings is the model building process, there's a higher level structure there. And this is what I call as the model selection triple. They need to tune and tweak around with the data and feature representation. They need to tweak around with the architecture. They need to tweak around with the hyperparameters. These three changes put together lead to a massive number of models being built. And it's not like it's an ad hoc process. There is AutoML heuristics for hyperparameter tuning that are widely used now. And so they specify a bulk set of models to train. One of the things I've been exploring over the last 5 years is understand that process more rigorously from the standpoint of ML users. How do they think about how do we go about building models? They don't think about just here's a computational graph, train it, and then they come back and then here's another computational graph from totally from scratch. They think about it in terms of changes they'd like to do to the data representation, changes they'd like to explore as part of the architecture. Like if you want to build a CNN on say time series data, which is something we did for public health use cases here on campus, there are certain classes of CNNs you want to explore, one-dimensional CNNs with certain number of layers. You have some intuition. So now you can train these models in bulk. The second issue I noticed was scalability was really not addressed that well in the open source world for PyTorch and TensorFlow. More recently, I think PyTorch distributed data parallel has been doing a better job. Horovod is doing a better job. But for a long time, it was not their primary concern. If you're operating on small data that fits on your memory, that's okay. And now with transformer style models, even models don't fit on GPU memory. And so we started looking at in the Cerebro project scalability from the first principles. How do you scale to very large data sets? How do you scale to very large models? How do you scale to large numbers of models being trained simultaneously in the model selection process? And so all of this put together is what I call high throughput deep learning systems, where we would like to perform model building at a higher level, but then the system now takes care of translating it to lower level computations for you. And this is a paradigm that's called logical physical separation. It's inspired by the database systems world. Like when you write an SQL query or when you write a transaction, you don't think about how exactly is it accessing the data, how exactly is it scaling to petabyte size data sets and so on. Or when you're writing a Spark SQL query or something like that. We want to bring that philosophy to the model selection world. You specify your model search process, you specify your model architecture in higher level tools. Keras, AutoML heuristics, they all allow you to do it in a very succinct manner. And so now Cerebro will be a middleware system that intercepts that and now translates the computations to TensorFlow and PyTorch executions for you by rewriting when exactly these computations are scheduled, where exactly they are scheduled. So now you could scale to very large data sets that may not fit on a single machine. You could scale to very large models that may not fit on a single GPU without needing to have that sort of systems expertise. You don't need to force ML users to understand how do you partition your workload, how do you scale your things, how do you stage out computations, and so on. And that is sort of the vision which we published at the CIDR conference earlier this year, the large scale platform for deep learning. That's the title, Cerebro, a large scale platform for deep learning. um, it gives us it kind of gives us this perspective of decoupling the what of the model building process from the how of the execution. And that is again inspired by the database systems philosophy of decoupling the what of the logic of the query execution from the how optimize and run the actual executions themselves. And so as part of the Cerebro project, once we've had this decoupling, we can now infuse several systems techniques, what we call multi-query optimizations techniques. That's jargon from the database world. Basically, what it means is you look across multiple model executions, see what you can share. You can share data access, can you share computations, and then that allows us to improve resource efficiency. It allows us to reduce runtimes, improve scalability, and so on. So that is what we've been pursuing in the Cerebro project over the last few years. And we've kind of gotten a long way through that, solving the data scalability challenge, solving the model scalability challenge. Now we are looking at kind of transfer learning as well. We're going to look at transfer learning is front and center in deep learning. It turns out that there is a model selection issue in transfer learning. You have to figure out which layers are you going to transfer from your pre-trained models, and that requires comparing different data representations, and that leads to redundant computations, that leads to scalability issues, and again, those are data systems issues, and that's sort of what we are tackling also in the Cerebro project.
And so Cerebro is it have elements of both the data, the build, and the deploy model? Does it live in all three of those, or is it primarily build and deploy, or just deploy?
I would say it's primarily build and deploy because in the deep learning landscape, I think the data preparation style issues are not as sophisticated as on tabular data. And this is an interesting dichotomy in the machine learning world. Most people don't use deep learning as much on tabular data. And a lot of business critical use cases are on tabular data, and they use boosted tree ensembles. I mean, the gradient boosted trees are still the most popular methods for machine learning. I saw the recent Kaggle survey. I keep track of the Kaggle survey, and random forests and boosted decision trees are still the most popular on tabular data. And so Cerebro is really focused on any neural computational graph, so things that can be expressed with TensorFlow and PyTorch and the like. And so that is primarily around unstructured and semi-structured style data, like time series, like images, video, audio, and so on. You could apply it to tabular data sets too, but I don't see that many use cases for tabular data sets in that regime. So Cerebro, that's why primarily focuses on the build stage and somewhat on the deploy stage as well. Over the next year, we're going to focus a lot more on the deploy stage by looking at cloud native execution for Cerebro. So there you will see a lot more integration with kind of cloud native infrastructure, serverless infrastructure, and so on.
When I hear you describe the Cerebro, what comes to mind is, something analogous to like a DSL for describing the way you want to deploy your machine learning models. Is that you're trying to raise the level of abstraction from thinking about, okay, I have a model, I want to put it here and here and here, to I have a model, and I have a model and I want it to serve this use case. Is that correct?
That is correct. Yep. I mean, that is, I wouldn't call it a DSL. We're not creating a new language. I would call it higher level APIs. So in the paper itself, we go over the kinds of higher level APIs we are aiming to support. There's some that are already popular that we don't need to reinvent the wheel there. Like AutoML heuristics are already popular for hyperparameter tuning. There's algorithms like HyperOpt, HyperBand, Asha, and so on. There's architecture tuning algorithms as well, like Google's NAS and AutoKeras and so on. All of these are basically DSLs if you wish. They are like poor man's DSL because they are APIs that under the hood produce different training configurations automatically for you. And so Cerebro would basically support these sorts of APIs on top. Now, for some of these evolving kind of emerging use cases like transfer learning, Keras and all these other tools like Hugging Face, they are coming up with APIs as well. And so those can be automatically kind of reused in the Cerebro context. Going kind of looking further ahead, we could actually construct a unifying TSL across these sorts of kind of environments to reduce the complexity of having to learn these multiple APIs. And that is certainly a possibility we would look at in the future.
And so is the core of Cerebro, is it kind of an expression of a workflow or a process, that starts from training a model, maybe invoking some kind of auto ML or architecture search, and then you need to deploy, going out to, figuring out, taking or creating that artifact and then pushing it out to some cloud service at that level?
Yep, that is correct. So you
Okay.
specify your model building workload at this higher level using these APIs. You could specify here's my compute cluster, and then the system would automatically figure out how to place those computations on the cluster for you. It could be provision cluster. We have integrated this with multiple backend systems. So you could run it on Spark, for example. We have integrated an open source that Cerebro Spark release is available. So if your data files are sitting on an HDFS and you're using Spark, you could do some ETL there, and then you could run Cerebro for training these models in that regime. We've also integrated this with Greenplum, which is a parallel RDBMS that Pivotal, now VMware, offers. And they have kind of shipped some of these ideas for their enterprise customers as well. So if your data sets are residing on the Greenplum warehouse, then you could actually run these computations there. You could also run this on native file systems. We are releasing a integration with Dask, and Dask is quite popular among data scientists these days for small clusters, less than kind of 10 nodes or something like that. So Cerebro can now parallelize your model building computations using Dask and offer all these optimization techniques that I'm talking about out of the box. And then in the future, in the next 1 or 2 years, our vision is to integrate this with cloud native infrastructure as well. So now you could say, here's my budget and here's sort of my cloud infrastructure. You could specify time budgets or cost budgets, and then Cerebro would also auto provision resources for your model building process. So that is part of our vision in the future. Um, Basically, ML users should not have to worry about systems and infrastructure issues. That is sort of the primary philosophy that is driving the Cerebro project.
What's the relationship between the user's data and all the rest of these things that they want to do in Cerebro? And so where does Cerebro start from the with relation to the data?
Oh, sure. So the data could be like I said, could be a set of files on a file system, which you want to use to build a model. Like a concrete use case I could give is with our public health use cases. Let's say they have accelerometer data, time series data that about a terabyte large. They have already labeled this data. So this is NIH funded work, and they were looking at building deep learning models to improve the accuracy of predicting user activities. Are they sitting? Are they standing? Are they walking? That sort of stuff. And in the past, they've built some kind of hand engineered physics based featureized random forest models. And they had about 75% accuracy for a binarized version of this task. We built these deep learning models using Cerebro that uses one dimensional CNNs and LSTMs on their data that hit accuracy of about 92%. And we published this in public health journals. The way to approach this is they have these data files that are partitioned and they are stored on a multi node cluster on campus. And so now, when we want to train these models on these data sets, you would invoke the Python API of Cerebro as from a client, like from your laptop or something. You would connect it to the machines that are available there. You would indicate these are the data files that you want to operate on. And then Cerebro would now take your TensorFlow code and automatically place it on these sorts of clusters. Make sure that you don't have to copy the data manually or anything like that. It doesn't need to replicate the data across workers for parallelization. And it would execute this process. It would surface the results to you. We are using TensorBoard for visualizing the results as well now. And so you could now monitor how are these models doing over time, and you could potentially stop some models, add some models in a human in the loop fashion on the fly as well. And so at the end of the session, you would have the models that you're interested in available with their accuracy, and then now you could do post processing with that. You could basically say, this is the model I want to choose. In our public health use case, they decided to do an ensemble at the end. They chose the top 3 performing models because their accuracy metrics, there were several accuracy metrics, and they kind of had Pareto optimal issues. And so that's sort of what we ended up with. So the part that Cerebro has abstracted away is having to worry about fitting these large data sets into your TensorFlow. Rather, you just specify your model architecture and your model building process, and then you get the output models at the end with their accuracies.
The next example that you discuss in your talk is a project called SortingHat. Can you tell us about that one?
Oh, sure. Now, SortingHat focuses primarily on the sourcing part of the lifecycle. And here, the primary concern we were looking at, I mean, again, there's a lot of issues in the sourcing part. We're not tackling all of these issues. One thing that kind of motivated me to look at this more is in the last few years, several companies are starting to claim they have automated the end-to-end ML workflow. And this, I mean, of course, model architecture search, hyperparameter tuning, feature engineering, there's several meta heuristics that have come about that are really good. They can automate it. The data preparation part, no, not so good. And so what I thought was happening was they were claiming something that wasn't actually really good. You can claim you have automated it, but if it is no good, what is the point of automation? And so what I decided to do was, let's create benchmarks. And this is a standard way for comparing tools, for testing their efficiency and testing their effectiveness and so on. And so here we realized what is missing in this landscape for vetting these sorts of claims is a suite of standardized task definitions and labeled data sets to figure out how well does auto data prep work today. And that is sort of what Project SortingHat is. It's very complementary, very different from the Cerebro landscape, which is really focused on system internals and scalability and stuff like that. Here, the focus is on understanding what are these data transformations that take place on tabular data before you can train an ML model, how much of that is automatable and how much of that is robustly automatable, and what are the implications if those automated steps fail, if they don't prepare the data correctly. How does it affect the model that you're building? What is the implications for the bias variance trade-off from a learning theoretic standpoint? So these are sort of the questions we've been looking at in this space. We published a vision paper on this. We've been creating benchmark tasks and data sets in this space, and we've been collaborating with some companies, Google and Amazon, and now OpenML as well, as part of this project.
Before we get to the specifics of the benchmarks and the data sets, I'd love some examples of where these automated data prep systems tend to fail. There are a number of them out there, both kind of academic open source as well as commercial. And, they will typically do things like, try to automatically bin your data or create, relationships between your features to give the, often AutoML model builders kind of more features to work with. But it sounds like you've identified some patterns where, those features don't work or don't create the results that are claimed. So elaborate on, where you see them failing.
There's this boundary between what I call data preparation and feature engineering. And so in the data mining and ML world, they have studied feature engineering where you come up with these transformed features or you do the binning of these things. So what we are looking at is actually even before that, which is you take your database that you get from your RDBMS or a data lake system, and then you just upload it to your AutoML tool as a CSV file. Now, what do you do with the first off, identifying what are the features present in the data? And that is the problem of feature type inference. That's the gateway step to data preparation. You need to identify, for example, your zip code of a customer, which is stored as an integer in your database or data file on a data lake. It's stored as an integer, but it's not a numeric feature for ML. You have to have either the user manually annotated, but many of these AutoML tools automatically infer the feature type by looking at the data, and they infer it wrongly. They will conclude that zip code is actually a numeric feature. Imagine giving zip code as a numeric feature to logistic regression, it could give you garbage results. Um, and so the first task we formalized was this feature type inference task. Given your data file and your attribute name and your values are present in the data file, let's say they upload it as a CSV to these tools like Einstein or SageMaker Autopilot or Google Cloud AutoML tables. They all allow you to upload a CSV file or a TSV file or a JSON file or whatever, but they all have these syntactic data types present. And so now they have to infer what are the feature types that are present in the table. So that's the first task. What we found was many of these tools fail when they are not able to distinguish between categoricals and numericals. And the zip code is a good example. It turns out to be a very common issue. There's product codes, there's health codes. So many categorical data are stored as integers because people like to encode them. And so these tools think of them as numeric features. And it turns out that there's a semantic gap there. How do you figure out something as a categorical? And so part of our benchmarks, what we did was we created these labeled data sets that metadata sets that annotated almost 10,000 columns from hundreds of data files that we collected from public sources. And we annotated them and we released them as labeled benchmark data sets. We then compared these tools against ML models. So now that we have formulated this task as multi-class classification, given a column in a data file, tell me what is the feature type. Is it categorical? Is it numeric? Is it timestamp? We created a unified vocabulary for type inference by studying all these existing tools in this space. And then we built simple ML models. Turns out that a random forest model, based on some statistics features and the name of the attribute, can beat substantially all these prior tools that were out there, like AutoGluon and Transmogrify and TFTV and Pandas and so on. And so that was the paper that published at Sigma this year. And that is the first task in the what we call the ML data prep zoo. That's the benchmark, the zoo of pre-trained models that we released, the data sets that we released, and the task definitions. Subsequent tasks, we are looking at some more, and we have published a vision paper laying out some common data prep steps that take place. The task that we've studied now is what is called category deduplication. When you have a categorical, like say state of a customer, sometimes they enter California as California, sometimes they enter it as CA. And now a data scientist is sitting and deduplicating these categories so that you don't end up with overfitting of the model. If you have too many representations of the same entity, you end up with overfitting. And so you sit and manually edit your data frame or your data file on Excel, trying to reconcile the value representation. That is a data prep step. And so now we are benchmarking that data prep step, trying to understand how does it affect ML accuracy if you do not deduplicate, and creating benchmark label data sets for these duplicate representations. And again, training ML models to automate that steps. So these are, they kind of seem like very low level grunt work, but it is these sorts of accumulation of low level grunt work that impedes the productivity of data scientists when they're working with tabular data. And if AutoML platforms aim to automate these things, you really need to understand where are they failing in these automation of these grunt work steps. And if they are failing, are they leaving a lot of accuracy on the table when they're building the automated ML method at the end? So that is sort of the kind of, I hope that gives you a good picture of what we are targeting in this space.
No, it definitely does. It definitely does. It also raises for me, obviously, similar questions happening at the feature engineering level. And I'm curious if there are benchmarks and data sets like what you're doing here applying to those types of systems. Seems like there are some opportunities there as well.
Absolutely. The data mining and ML world have been studying some of those automation of feature engineering, automation of algorithm search, and hyperparameter tuning. And there are benchmarks, like OpenML itself has a benchmark suite for those kinds of things. And so what we found to be this big gap was really in the data prep stage. And I think the reason for that, again, going back to our original theme, database and ML communities have been so far apart that this thing fell through the cracks. The ML community understood feature engineering. They understood algorithm search and hyperparameter tuning. So they were able to create benchmarks for that. The ML community did not appreciate the data prep stage because they thought, oh, that's just grunt work. But then it turns out that the database community understands that grunt work for like 2-3 decades, because we've studied data cleaning and data integration and data ETL and transformation and so on. So this is another area where I think the database community and the ML community need to come together and work together. And I ran a panel discussion at SigMod this year focused on this topic. There is a blog post out on it on the SigMod blog, so I would encourage your listeners to check that out too, where I hope over time the research community in both ML and DB work together to understand this data prep space better. There's also this data-centric AI workshop that Andrew Ng and others have launched. That's right after this DB AI workshop. That also looks very exciting. So I'm glad that there is more attention to data-centric issues in the ML world as well. We really need to understand the way the data is modified, the ways data is edited. How does that affect ML, and how do we make that process more systematic? How do we create tools that make people more productive in doing that sort of stuff? I think that's a big opportunity at this intersection.
What do you think needs to happen in order to kind of gather more momentum at this intersection? Does it kind of teaching database people more about machine learning, teaching machine learning people more about databases, or all of the above? The
I
answer
think
is
it's
always all of the
all of
above.
the above. That is correct. And that kind of is a good segue for the last section of my talk, where I say, how do we go? Where do we go from here? And so I
Okay.
give avenues that ML people can learn about some of these techniques from the database world and vice versa. Conferences and publication avenues. There's this scalable data science track at VLDB and Sigmod now, where you can publish this kind of stuff. NeurIPS also has the data sets and benchmarks track where you can publish this kind of stuff. There's the MLSys conference. So this is kind of new community to nurture this sort of research that has formed. And coming to these sorts of workshops will allow you to exchange ideas with people from multiple areas and create this sort of synthesis of these areas that is needed. Um, Apart from that, I mean, in terms of community efforts, these workshops will hopefully spur conversations on creating more standardized task sets and benchmarks and data sets. And I hope the industry companies that are building these sorts of tools also participate in these conversations. It has had a transformative impact in both the database and ML worlds. Like ImageNet, for example, was a defining kind of pivot point in the ML, the history of the ML research industry, research world and industry. In the database world, we've had the TPC benchmarks, which were a pivot point for how the database industry was shaped. And so in the data prep landscape, I think there really needs to be a push towards these sorts of understanding of what are the common tasks and what are the sort of benchmarks that we should strive towards. How do we evaluate these sorts of tools on a comparable basis, on an even footing? These are sort of some questions that I think these community efforts will hopefully lead to resolutions.
Awesome. Awesome. Well, Arun, thanks so much for joining the podcast and sharing with us.
It was a pleasure. Thank you again for having me, and thanks for all these questions. And I hope the audience enjoys the NeurIPS conference and the DBAI workshop. And I look forward to seeing more people there.
Awesome. Thanks so much.
Thank you, Sam. Take care.